This is a walkthrough of a AS Further Maths Decision 2 paper. Question 1. The table below is a cost matrix for an allocation problem. The total cost is to be minimized. Each of the workers A, B, C and D must be assigned to exactly one of the tasks P, Q, R and S. It is not possible to assign P to R or C to S. Part A. The table must be adapted before the Hungarian algorithm can be applied. Part 1 of Part A, explain how to adapt the table. So we need to add values which are at least twice the maximum value, at least twice the maximum value. Now, the maximum value in this table I can see is 21, so at least that needs to be at least 42. So let's say e.g. 50. So I would put 50 here and 50 here, for example. Part 2 of Part A, explain why this adaptation allows the algorithm to be used to solve the problem. So what happens is that this makes the particular allocations what we call unattractive to the algorithm. Unattractive. Need to learn how to spell unattractive. Part B. Reducing the rows first, use the Hungarian algorithm to obtain an allocation which minimizes total cost. You must show the table after each stage. We must also explain how you know whether you have reached an optimal result, and also state the final minimum cost. So step number 1, we're going to start with row reduction. So we need to start by finding the smallest values in each row. And the smallest values in each row, in row A it's 6, in row B it's 8, in row C is 6, and row D it's 11. So this value needs to be subtracted from every row. Before we do that, let me put in these values. As I said, I'm going to use 50 to make these allocations unattractive. So I start with row 1 and I'll take away 1 from each of those. 6 from each of those row values. So I have 1, 2, 12, 0. The second row, I'll take away 8 from each of these values. That will give me 0, 13, 42, and 4. Row C, take away 6 from each of these values. I'll have 0, 11, 3, and 44. And then in the bottom row, I'll take away 11 from each of these values. And so that will leave me with 5, 9, 2, and 0. Now step number 2, I'm going to do column reduction. So I want to find the smallest values in each column. And they are 0 for the first column, 2 for the second column, 2 for the third column, and then 0 for the fourth column. So I'm now going to subtract those values from each column. So the first column is going to remain the same because I subtract 0, so they'll remain unchanged. So I'll have 1, 0, 0, 5, 0, 0, 5. In the second column, I'll subtract 2 from each of those values. So I'll have 0, 11, 9, and 7. Third column, subtract 2 from those values. So 10, 40, 1 and 0, and the last column subtract nothing, so I have 0, 4, 44 and 0. Okay, I want to now see what's the minimum number of lines required to cover all of those zeros. So let's put this in a sort of green highlighter pen. So I'll need one line there, I'll need one line here and one line here. Okay, so I've got a minimum of 3 lines required to cover all the zeros. So since 3 is less than 4. And remember, the 4 comes from the dimension of the matrix, which is 4 times 4. Since it's less than 4, we have not found an optimal solution. So we have not found an optimal solution. And it can be improved, which is what we're going to do now. Now, the first thing we do is look for the smallest uncovered element, and that is 1. So we now augment the reduced cost matrix by 1. So first of all, we start by any element which is covered by 2 lines, we increase by 1. So that means the allocation of A and P gets increased by 1, and D and P gets increased by 1 to 6. Any elements that are just covered by 1 line remain the same. So the 0, 10 and 0 on the top line remain the same, and the 7, 0, 0 on the bottom remain the same, and the 0, 0 in the first column remain the same. And then any uncovered elements get reduced by 1. So 11 will become 10, 40, 39, 4, 3, 9, 8, 1, 0, and 44, 43. So now we do the same thing again. We see how many lines, what's the minimum number of lines required to cover all of the zeros. So let's see, we need 1 line across the top, 1 line in the first column, 1 in the bottom row, and also to cover that 0 that's in the third column, we need a line here, 4 lines required. So since 4 lines are now required to cover all the zeros, the solution is now optimal. So we have an optimal solution here. So let's now look at what allocations we can do. Okay, so we're looking for the zeros in the table. So if we start with A can be allocated to Q or S. So I'll just put A here, and it can be allocated to Q or S. If we move on to B can only be allocated to P. So that choice is made for us. C can be allocated to C, P or R. So C can be allocated to P or R. And D, that can be allocated to R or S. So R or S. Okay, now since B can only be allocated to P, then that means we can't allocate C to P. C has to be allocated to R. Since C has to be allocated to R, D can't be allocated to R. D has to be allocated to S. And I'm not sure why I put B here. It should be A is allocated to Q or S. I need to learn my alphabet. Since D is allocated to S, that means that A cannot be allocated to S. It has to be allocated to Q. So my final allocation, let's do this here. So final allocation is going to be A with Q, B with P, C with R, and D with S. Okay, so let's just highlight that. The next thing that I need to do is to work out what the cost of those allocations are. So going back to my original cost matrix here, so A allocated with Q is a cost of 8, and then B with P, that's also a cost of 8. C with R is a cost of 9, and D with S is a cost of 11. Okay, so my total cost is going to be equal to 8 plus 8 plus 9 plus 11, and that's going to give me a total cost of 36. So that will be my final solution for this question. Question 2, Part A. In the context of game theory, Explain what the term play safe strategy means. So each player looks for the worst that can happen if they make each choice in turn. The player then picks the least worst option. They want to minimize their losses. A two-person zero-sum game is represented by the following payoff matrix for player A. So this is from player A's perspective. Part B, verify that there is no stable solution for this game. So we're going to start by writing down the minimums for each row. And that's going to be -4, -2, -1. And then the maximum for each column, and the maximum for each column is 4 and 3. And so we'll start with the row maximum. So the maximum minimum is going to be -1. And then the column minimax, so the minimum maximum, is 3. Now, since -1 is not equal to 3, in other words, the row maximum is not equal to the column minimax. So by the stable solution theorem, the game has no stable solution. Part C, and part 1 of part C, find the best strategy for player B, defining any variables you use. And then once we've done that, we're going to find the value of the game to player A. So the first thing we're going to do is, because we want to find a best strategy for player B, we're going to rewrite this payoff matrix from player B's perspective. So here's the new or transposed payoff matrix from B's perspective. So we're going to let player B play 1, so the little sub 1 there just means they're going to be play 1. And this means like they're going to play 2. Let's say that they play 1 with probability P, and they play 2 with probability 1 minus P. So let's write that down. Then that means that player B knows that player A has 2 options. Okay, so what are A's 2 options? Well, if A plays column number 1, then B's expected winnings are, let's write those down, they're going to be in terms of P. So 4P here, 4P, minus 3 times by 1 minus P. So 3 times by 1 minus P. We'll simplify that, and that becomes 7P minus 3. Okay, now if A plays column 2, that means that B's expected winnings are going to be -4 times by P, and then plus 2 times by 1 minus P, and that will become 2 minus 6P. And now we're going to look at when A plays column 3, so I'll just shorten it to this, A3, and write down what B's expected winnings are, just shorten it to this for space. So it'll be minus 2P, and then plus 1 times by 1 minus P, and that simplifies to 1 minus 3P. So let me just highlight these for now, because I'm going to need these when I draw the graph for these. So 7P minus 3, 2 minus 6P, and 1 minus 3P. So I'm just going to clear off some of this at the top so I've got a bit of space to draw the graph in. Okay, here's my graph ready. So I'll start with the 7P minus 3. So remember, we're going to substitute in P equals 0 and P equals 1 and work out what the two ends are. So if I substitute in P is equal to 0, I get -3. So I'll put a little mark here. That's going to be one end of the line. And then if I substitute 1 into this, so to get the value on this end, so that would be 7 times 1, 7 minus 3, which is 4. And so I'll put a little dot here on 4, and now I'm going to join them up. Okay, I'll move on to the next one here, which is 2 minus 6P. So again, start by substituting 0 into this. I end up with 2. Let's do this in a different color. So a little dot here at 2 at the p equals 0 end, and then at the p equals 1 end. So 2 minus 6 times 1, 2 minus 6, that's going to be negative 4. So down here, and then I'm going to join those two dots up. Then the last one is going to be 1 minus 3p. So again, I'll substitute 0 into this, and then I'll get 1. Which colour should I do that in? Let's do that in green. So that's going to be here on the p equals 0 end, so just there. Substitute 1 into this, so 1 minus 3 times 1, 1 minus 3 is going to be negative 2. So that is going to be here, and again, I'll join those up. So I'm looking for the highest point of intersection between the two lines that has no lines beneath it, and that's just about, you can just see it, the intersection of the red and blue line. So that's the intersection of 7p minus 3 and 2 minus 6p. So now what we need to do is to solve those simultaneously. So 7p minus 3, we're finding the intersection of those two lines, is equal to 2 minus 6p. So we can rearrange that, add 6p to both sides, we'll get 13p. Add 3 to both sides is equal to 5. So that gives me a value of p equal to 5 over 13. So that means that player B should play 1 with that probability, 5 over 13, and play 2 with probability 1 minus 5 over 13, which is 8 over 13. So now we can do the last part of part C, which is to find the value of the game to player A. Okay, so the value of the game to A is, now we can use either one of these, the 7p minus 3 or the 2 minus 6p, to work out that value. Now remember, this p is from B's perspective, so whatever we work out for the value is going to be the value for B, so we need to reverse that and put a minus sign in front of it. So we basically need to do the negative of 7p minus 3, otherwise we'll be working out the value to B. So it'd be negative, and then 7 times by, so P was 5 over 13 minus 3, and that gives 4 over 13. If we didn't put the minus in, we would have got the value of the game to B, which would have been negative 4 over 13. Now if I had used 2 minus 6p in here instead, I would have got the same result. Question 3. Figure 1, that's figure 1 here, shows a capacitated directed network. The number on each arc is the capacity of that arc. The numbers in circles represent an initial flow from S to T. Part A, explain why the dotted line marked K1 in figure 1 is not a cut. Okay, so let's just highlight that so you can see. So K1 is here, that's this dotted line. So basically K1 is not a cut because a cut must separate a network with source on one side of the cut and the sink on the other side of the cut. K1 has the source and sink on the same side. So we'll have a look here. So you see the source and the sink, now both on the same side. So that's why K1 is not a cut. Okay, two cuts C1 and C2 are shown in figure 1. So C1 here, let's highlight that. So there's C1, and C2, let's highlight that in a different color, is here. Okay, like that. And in part B, what we need to do is to write down, first of all, the capacity of each of the two cuts, C1 and C2. So we'll start with the capacity of cut C1. So we want the total capacity of the arcs flowing from source to sink. So we have 1 here, so we've got 13, and then here 11, and then here we have 2, and here we have 10. So we just need to add those up. So it's going to be 13 plus 11 plus 2 plus 10, which gives a value of 36. So now let's look at the capacity of C2. So let's have a look at which arcs they are. So flowing from one side of the cut to the other. So we have 13 here. What else do we have? We've got 14 here. And 8 here. So we'll just add those up. 13 plus 14, that's 27, plus 8, that's going to be 35. So that's the first part of part B. So the second part of part B is the value of the initial flow. So to do that, we need to look at the initial flow out of the source, and we've got 6, 9 and 7. So 6 plus 9 plus 7, that is 22, and that should equal the flow into the sink. So let's just check that. So that'll be 3 plus 14 plus 8. So 3 plus 14 plus 8. Sorry, not 8. It's not the maximum flow. It should be the actual flow. So it should be 3 plus 5. Sorry, 3 plus 14 plus 5, not 8. And that does equal 22. So that would be the value of our initial flow. Part C. Complete the initialization of the labeling procedure on diagram 1, and diagram 1 is here, in the answer book, well it's here, by entering the values along arcs SA, AD, DE, GE and GT. So let's just highlight those arcs. So SA, AD, DE, EG or GE and G to T. So let's start with arc SA. So we need to look at its current capacity and what the full capacity can be. So that arc can be increased by a capacity of 7 or reduced from 6 down to 0. AD, we have a capacity increase of 7 possible here, and it could be decreased by 4 down to 0. Then we'll look at arc DE. So DE, we've got a capacity of 5, we're actually at 1, so we can increase by 4 or decrease by 1. Arc GE, so we're along this one. So this arc has a capacity of 8, so it can actually be increased by 8 or decreased down to 0 because its current capacity is actually 0, so it can't be decreased anymore. And then G to T, so this can be increased by capacity of 8 and decreased by 3. Part D. Hence use the labeling procedure to find a maximal flow pattern for the network. And it's saying to us that we must list each flow augmenting path you use together with its flow. Okay, so we'll do that first before we move on to the second part. Now, first thing I'm going to do is to see if there are any saturated arcs, and there is, and they're not going to form part of my route. So E to T is saturated and E to F is saturated. So these are routes which cannot be increased anymore. Right, let's have a look for a route that I can increase. S, A, D, D, T looks like a nice one because I can get 7 by increasing that. Because I can increase by 7, increase by 7, increase by 9, increase by 8. So the maximum of that is 7. So I'm going to increase, and that is S, A, D, D, T. by 7. So let's update the labeling when we do that. So we'll get 0 and 13, 0 and 11, 2, 10, 1 and 10. So now I've saturated SA and AD. So let's highlight those as roots that we are not going to use. And looking for a root that I can increase. Now if I went along SB, wherever I go next, the most I can increase it by is 2. However, if I do SCFT 733, I can increase that root by 3. So let's just highlight that root so you can see which one I'm talking about, and then write down that we're going to increase SCFT by 3. Okay, so let's update the labeling when we do that, and so that will be 4, 10, 0, 10, 0, 8. Right, so now I've saturated 2 more arcs, which are CF and FT. And let's do those in the same color as the other one so it doesn't cause confusion. So stick it all in orange. Okay, now whichever route I take, I'm going to have to go G to T, and I'm only going to be able to increase that route by a maximum of 1, and I'm going to have to use like one of these routes going backwards to get to T, to get to the sink. Okay, let's see. So S, B, E. Now I can't go backwards along EG or GE, because when you go backwards along a route, you want to decrease the reverse number there in sort of, as you're talking about, like it's forward. So this is like the reverse one there. I need to be able to decrease it by 1. I'm not going to be able to do that here. So let me highlight that route here. So this is just a highlighted route. And then we'll just write down that we're going to increase S, B, E, D, G, T by 1. That's the best we can do. Okay, so let's update the labeling when we do that. So increasing by 1, we will get 1 and 10 here, and then 3 and 6. Going backwards along this arc here, where we would decrease the forward number there, the amount we would increase it by 1, we now do the opposite. So we increase this reverse one by 1. Sorry, so that'll become 0. 1 minus 1 is 0. So decrease by 1 here, increase by 1 here, and then when we get along the top here, we just go back to normal. So 1 and 11, and then here 0 and 11. So that means we now have another saturated arc, which is GT. So we cannot perform any more augmentation. Okay, now we can move on to part 2 of part D. Show your maximal flow pattern on diagram 2 in the answer book. So I've highlighted all of the numbers that need to go onto this diagram, and any arcs which are saturated are going to be circled. Those numbers are going to be circled. So SA is 13, and I circle that. In fact, all of my routes which are highlighted in this orange color are saturated. Okay, so let me complete the labeling of this. So 10 and 10 here, neither of those are saturated. AB, oh, I didn't highlight that one. That's going to be this number here, the 2. So we've got 2 here, and then 0 here, Now I don't think I highlighted that one, so I'll highlight that one here. Then it's going to be 6 and 6, 10 down here, circle that one because that's saturated, 8 over here, saturated, there's another 8 over here, that's saturated, 14 E to T, saturated, G to T, 11, saturated, D, G, that's saturated there, AD is also saturated. Anything else? D, E, that's going to be 0, and GE is also 0. Part E, first part of part E, is to state the value of the maximal flow. Okay, so I either need to look at the sum of the flows out of the source, which should equal the sum of the flows into the sink, and if I add either one of those up, I'll get an answer of 33. And the second part of part E says prove that your flow is maximal. Now, to prove that this flow is maximal, I need to use the maximum flow minimum cut theorem, and I either need to find a cut through empty arcs from T to S, which I can't do, or saturated arcs from S to T, and that's possible to do that. I can put a cut here, and that goes through 3 saturated arcs, GT, ET and FT. So summarizing that, I would say that a cut through the saturated arcs GT, ET and FT has a value of 33. That's the 11 plus 14 plus 8, which I worked out already. Therefore, by the maximum flow minimum cut theorem, the flow is maximal. Question 4. Rebecca invests a sum of money in a savings account which earns 3% interest per annum. At the end of each year, she withdraws £600 to pay for her grandson's music lessons for the following year. Let Xn represent the amount remaining in the account at the end of the nth year after the interest for the year has been paid and £600 has been withdrawn. This information is represented by the recurrence relation Xn is equal to 1.03 x n minus 1 minus 600, where n is greater than or equal to 1. Part A, find a general solution for this recurrence relation. Okay, so because of the form that it's in, and it's in this form here, we'll start with the complementary function. And a general solution for the complementary function is going to be in this form here, where c is a constant. So we're going to have c, and then a is, in this case, 1.03 to the power n. Then we'll move on to our particular solution. So the form of g and n, it's just a constant, so we're looking to try lambda for this. So xn is equal to lambda. So now we want to calculate lambda, so we're going to substitute it into the recurrence relation. So we'll have lambda is equal to 1.03 lambda minus 600 minus 600. So that will give us 0.03 lambda is equal to 600. And then if we divide both sides by 0.03, we'll get lambda is equal to 20,000. So our general solution is going to be our complementary function. So we'll write xn is equal to c times by 1.03 n plus 20,000. Okay, Let's continue. Given that Rebecca has invested £4,000 into the account at the start of the first year, part B, use this information to find a particular solution for this recurrence relation. Okay, so we basically want x0 to be 4,000. So if we substitute n equals 0 into this, we'll get 4,000 is equal to c times 1.03 to the power 0 plus 20,000. So that will give us 4,000 minus 20,000 is equal to c, which means that c is negative 16,000. So that now gives us our particular solution. So we'll replace that c with negative 16,000. So we'll now get xn is equal to negative 16,000 times by 1.03 to the power n plus 20,000. Okay, let's move on to part C. Find the year in which the funds in the account at the end of the year fall below £600. So part C is basically trying to solve this when xn is less than 600. Okay, well, we know what xn is, so that's negative 1600 times by 1.03 to power n plus 20,000. When is that going to be less than 600? We'll start by taking 20,000 away from both sides. We've got negative 16,000 times 1.03 to the power n is less than, now that'd be 19,400 or negative 19,400. We'll get rid of the negatives from both sides, which means that we need to flip the sign and then make it greater than. Then we'll divide both sides by 16,000. So 19,400 divided by 16,000 actually becomes 97 over 80. Now we'll do log of both sides. Now when we do log of both sides, we'll have log of all of this. We'll bring the n to the front. So it'll be n log 1.03 is greater than log 97 over 80. Let's carry on the working up here because I want a bit more space. So n is going to be greater than the log of 97 over 80 divided by log 1.03. Let's see what that gives us for n. So that's 6.5186 and so on. So n has to be a year, a number, so that's n equals 7. So that's going to be in the 7th year, or the end of the 7th year, so 7th year n. So let's just highlight that answer there, and we're done.